Hi there, this is Miss Mantle, and today we're going to be talking about the definite integral. We're going to continue our discussion of the definite integral and talk about properties of the definite integral, and then we're going to learn the most fun theorem of all, the fundamental theorem of calculus. I'm going to show you both parts of the fundamental theorem. You do need to know both parts. Some books call it part one and part two differently than our book does. So I'm kind of used to calling them part one and part two, but know that if you go elsewhere that you might end up calling them different parts. But what's more important is that you understand what they do. Very important part for this entire semester. So to get started, we have an opener here. You're asked to find a right Riemann sum with 3 subintervals to approximate the area under the curve, estimating the distance traveled. Okay, so if you're watching this video at home, I would suggest that you take this, pause the video and see if you can do the opener. Give yourself like no more than 10 minutes. I don't think you even need that much time. And then come back and let's see how you did. Okay, so we're using a right Riemann sum with 3 subintervals to approximate the area. Now, the first thing that I notice is that my time intervals are not consistent. Whoopsie, I need to get my pencil going here. I notice that my time intervals are not consistent. So even though I'm going from 0 to 6 with 3 subintervals, I can't take 6 minus 0 divided by 3. That's a big no. We do not have equal subintervals. And so what I mentioned last time in our notes was that we need to calculate each rectangle. Okay, so we're doing a right Riemann sum. And so the first rectangle is going to go from 0 to 2. So that's going to be a delta x value of 2. This is delta, well, I guess I should say delta t. And then the right, looking at these two values here, the right point is 4 because I'm ignoring what's happening at 0. I'm only giving the function value at 2. Okay, the next rectangle from 2 to 5, I guess I should write it like in interval notation. So from 2 to 5, it has a delta t value of 3, that's delta t, and then the right endpoint would be 2. And then the third rectangle is from 5 to 6, and so my delta t would be 1, and 1.2 for my function value. This is 15.2, and my units here, I'm multiplying a delta t, which is in minutes, and I'm multiplying by a velocity in feet per minute. My minutes units will cancel. I'm left with feet, so 15.2 feet. Next, write a Riemann sum using limit notation representing the shaded area under the curve. Okay, so we're given the function, and it says use right endpoints with equal subintervals. Okay, so let's see, we are going to go from 0 to 4. So delta x is going to be 4 minus 0 all over n, or 4 minus n, 4 over n, excuse me. We're starting here at 0, and so I'm going to go over 4n. So I'm starting at 0, and I'm going to go 4 over n. And I'm going to do that every time. Okay, now I know that, like, I don't know, it doesn't mean only 4 rectangles. It means I'm doing this as n goes to infinity. And so this means that my function is going to be starting at 0 and then going 4 over n every interval, and then I number of times. All right, so let's kind of zoom in a little bit here. And so this is going to be the limit as n goes to infinity, sigma I equals 1 to n. And then my function, if I go back and look here, is ln x plus 1. So that's going to be ln quantity. I started at 0. I'm not going to write 0. I'm just going to write 4I over n plus 1. My delta x value is 4 over n, and then I need to make sure to say which interval I'm on from 0 to 4. So here is my answer. Okay, lastly, it says calculate L2. So that means left rectangular approximation method. And don't use your calculator, so that probably means my answer is going to be in terms of pi. Okay, so we're going to need L sub 2. I don't know why that's in blue. Let's go back and make that black. L2, that means I'm going to have 2 rectangles. And what I need is my delta x, and then I need my f of x sub 1. And then I'm going to have delta x, and then my f of x sub 2, whatever that happens to be based on delta x. So delta x is going to be pi minus 0 all over 2, because I'm doing from 0 to pi and then 2 rectangles, so pi over 2. And so if I just sort of think about, like, I'm starting at 0, I'm going to pi, my first rectangle is going to be from 0 to pi over 2, and my next one from pi over 2 to pi. So delta x is going to be pi over 2, and then I need to find out what is f at left endpoint would be 0, not pi over 2. And so that means 2 plus sine 0. Well, the sine of 0 is 0. This is just 2. So that's 2. And then f of, on the second rectangle, my left endpoint is at pi over 2. So it's going to be 2 plus sine pi over 2. Pi over 2 is 1, so this is going to be 3. So my delta x value is pi over 2, and then 3. So this is going to be 5 pi over 2. And that's it. Let's go ahead and turn the page. Okay, so the thing about integrals is we always want to make sure that we're talking about area under a curve, area between the function and the x-axis. So we talked about this last time, but just reminding you that you've got this integral symbol, which means the sum. And a and b are your limits of integration. The a is what we call the lower limit of integration, and b is the upper limit of integration. Remember that f of x stands for the height of my function, and that dx is representing the width, or delta x, as delta x goes to 0. And area, quote, under the curve really means between the function and the x-axis. And what we talked about last time as well was that axis, I can't spell, is that we can have areas or integrals that are positive, integrals that are negative. Depends on where they are. Okay, now here's a little something. It says x is a dummy variable. In this integral notation, in this notation here, this represents area. As long as I have limits of integration that are numerical, this thing that we're calculating is an area. And so it doesn't depend on what x is. And so that means that we can replace the variables without changing the value of the integral. So as you can see here, we have the integral of f of x dx, or the integral of f of t dt, or the integral of f of r dr. They do have to, the variables have to match there. I can't say f of r I can't say f of r dt. That doesn't make any sense. So that's definitely not allowed. You cannot say from a to b f of, x dt. That's like super bad. But again, the area here, or the integral, represents an area, and so the variables don't really matter. It's a dummy variable, but they do have to match. Okay, so let's talk about some properties. The properties of definite integrals are super important. Oftentimes, multiple choice questions on the AP exam will pertain to the properties of integrals. Okay, so we have the first property, and I don't care if you know the numbers of the properties, that's not important, but it's, do you understand what they mean? So I've got the integral of f of x dx from a to b. Notice that that's equal to the opposite of the integral from b to a. So for example, it's not proper to say the integral from 5 to 0. We always want the lower limit of integration to be on the left. And so what this is telling me is that if I get an integral, sometimes you'll be given this integral, and all you have to do is you just flip it and make it be from 0 to 5, and then you can call that negative. Right? This is like not good. Okay, next. This one is saying that the limits of integration, if I have some function, whatever it may be, and I'm going from a to a, well, remember, it's area under the curve. If I'm going from a to a, like there's no area. This is 0. There is no width, right? There's no width. There's no delta x. I can't do b minus a all over n as n goes to infinity. Like there's nothing there. That would be 0. And so if you are going from a to a in your limits of integration, that's equal to 0. Number 3, if I am integrating a constant, then it's just c times b minus a. So if I have a constant, here's my function, and the constant is c, and I'm going from a to b, finding this area under the curve. Well, it's just a rectangle. And so the area of the rectangle is our height times delta x. Well, the height is c, and delta x is b minus a. And so that's why this is our integral. Here, I'll zoom. I kind of did that quickly, but here you go. All right, number 4. Notice that you've got a constant in front of a function, and it's equal to the constant times the integral. So this just means that if you've got a constant, you can pull it out into the front. Oftentimes, it just makes life a little bit easier to just get that constant out of the way and evaluate the integral. Number 5, pretty straightforward. If I'm going to take the integral of the sum or the difference of two functions, I can do them separately, just like we did with limits. And then this next one is sort of like a common sense kind of thing. This is saying, let's say I have some function, and it says my function, I'm going to go from a to b. Let's call that area 1. And then it says to that, add the integral of the function from b to c. Call that area 2. Well, isn't that the same thing as just saying the area is from a to c is just area 1 plus area 2? So if I know the area of 1 and I add it to the second one, it's the area of the whole thing. That's all this is saying. This 6th one here is kind of one that shows up a lot on the AP exam. And we're going to take a look at some problems like that in just a second. Let's turn the page. Okay, really common kind of question. You're given some information about some integrals, and you're asked to evaluate some properties. Okay, so I'm looking for the integral from 1 to 3. Okay, now I'm going to just kind of think about what's happening here. So I'm looking for what's happening from 1 to 3. I want to know what is this area under the curve. Well, given what we have above, it tells me that from 1 to 4, that the area is 10. And from 3 to 4, the area is -3. And so this is like writing a little variable equation, but I'm using integrals instead. I could say that the integral from 1 to 3 of my function plus the integral from 3 to 4 of my function is equal to the integral from 1 to 4 of my function. Now, some of you probably don't need to do this. This is unknown. I don't know what this is. Maybe I'll call it A. Oopsie. And then from 3 to 4 is -3, and from 1 to 4 is 10. And so I'm just going to add the 3 to both sides and get 13. And so then this is equal to 13. Okay, so similarly, you could have just moved, this term to the other side and written it, I'll write it a little bit smaller here maybe if I can. The integral from 1 to 3 f of x dx is equal to the integral from 1 to 4 f of x dx minus the integral from 3 to 4 f of x dx, right? That's basically what we did. All right, let's move over to part B. This one's saying the integral from 4 to 3. Well, we know the integral from 3 to 4 is -3, and I also have a constant, a 7 there. So I can do a couple of things. First, I'm going to move the 7 out to the front, f of x dx. And then I don't like the limits going from 4 to 3. I want them to go 3 to 4, but if I do that, I need a negative out into the front. Okay, and we know that the integral from 3 to 4 is -3. And so then this is 21. Okay, so we can do another example that, maybe is a little bit more complicated in terms of what the integrals are equal to, but this applies to any integral, whether they're just simple functions in function notation, in just variable notation, or whatever. So this one, we're given the integral of e to the x dx from 1 to 3, and that's equal to e cubed minus e. It wants us to evaluate the integral from 1 to 3 of e to the x minus 1. Okay, well, according to the property number 5, if I'm adding or subtracting, I can break apart my integral into 2, like so. So I can just break them apart, and then that means that I can evaluate them separately. Okay, this integral here from e to the x dx from 1 to 3, that was given in the problem. That is e cubed minus e, minus whatever's happening over here. Okay, over on the right-hand side, this is telling me f of x is equal to 1. So that looks like this. I can always draw it if I'm not really sure what's happening, especially here at the beginning. 1, 3. Oh, right, it's just a rectangle. And so the rectangle here is going to have a height of 1, and then 3 minus 1 for the width. And so e cubed minus e minus 2. And then that's all I got to do. Let's turn the page. Okay, here's where the fun stuff starts. What if I don't want to go from just 0 to 2 or from 1 to 3? I want to go, I have a function f of t equal to 3t, and I want to go from 0 to x. So I want to cover the whole thing. So since x can vary, we can think of this integral as the area under the function so far. So that means that it's a function. That means that we can find out what this area is at any given value of x. So this function that I have here, if this is t and here's f of t, then I gotta zoom in here. Then I have f of t equal to 3t. It's just a linear function with a y-intercept at 0 and a slope of 3. And I'm starting at 0 and I'm going to x so that I'm finding this area. But this area can change depending on where x is. Well, this is just a triangle. And so I can find the area of a triangle, 1/2 base times height. 1/2. All right, well, my base is whatever this distance is, and that's going to be x. And then my height is going to be the value of the function at x, which is 3x. So this is 3x. And so my area is going to be 3x squared over 2, which is a new function. G of x is our new function. So here's what it looks like. We have the integral from 0 to x 3t dt is equal to 3x squared over 2, which is a new function. So super duper, let me fix that so it's not so crappy. Here we go. Okay, now let's compare f of x, which is 3x, and our solution, g of x. If I can move this over, g of x, which is 3x squared over 2. We want to think about how are they related to each other in a calculus sense. And I'm hoping that you're thinking about derivatives. If we take the derivative of g, we'd have 3 times 2x all over 2, which is 3x. Like, woohoo! That's like a super duper important relationship. When we integrate and get a function for g of x is an antiderivative of f of x. That means that if I take the derivative of g, I'm going to end up with the original function. So if g of x is equal to, oh my gosh, here, the integral, let me fix that and put a better color. If this is the integral from 0 to x f of t dt, then g prime, so if I take this expression just as I've written it and I take its derivative, I'm going to be taking the derivative with respect to x of the integral from 0 to x f of t dt, and that's equal to f of x. Okay, that is one of the fundamental theorems of calculus. So the question is, how do we go about finding this algebraically without graphing? Like, we're going to be doing some more complicated functions, and it's not just going to be a simple triangle or square or rectangle or whatever. So let's go ahead and develop, what's called the fundamental theorem of calculus. All right, so let's go back again. So we said that if g of x is equal, okay, now notice that I've replaced the 0 at the bottom with a. That's okay. It can be any number. It doesn't have to be always at 0. It can be at any constant. So this right here is any constant. Okay, so if g of x is the integral from a to x of f of t dt, this means that if I take the derivative of g, I'm going to equal f of x. Okay, Now, if capital F is another antiderivative, right? This right here is an antiderivative. Antiderivative. So when we talked about antiderivatives in the last semester, we said that antiderivatives differ only by a constant. And so I could have another antiderivative plus a constant, and that could be equal to the other antiderivative because antiderivatives differ only by a constant. Right, so when we talked about here, I'll just make a little side note here and then I'll erase it. But when we talked about like, I've got x squared and its derivative is 2x. Okay, well, if I gave you 2x and said, well, what is its antiderivative? We said, well, that's going to be x squared, 2x squared over 2, which is just x squared, but plus c. So I could have one antiderivative be x squared plus 5, and this one be x squared minus 2. And if I add 2 to both sides, then I'd have x squared plus 7 equals x squared. So they're the same function, they just differ by a constant, and the constants have been combined onto into it the same constant. Okay, I'm going to erase that there. All right, so we're trying to derive the fundamental theorem. Okay, so let's kind of summarize what we're saying here. We're saying that g of x is the integral from a to x of f of t dt, which is also equal to a different antiderivative plus a constant. These differ only by a constant. Okay, so this is our main statement here. G of x is an antiderivative, which is another name for an integral. And so let's plug in if x is equal to a. So I'm going to take this whole statement, and everywhere that there's an x, I'm going to plug in an a. So I'm going to say a to a, f of t dt equals f of a plus c. Okay, well, let's think about what this means. Well, what is the integral of f of t dt from a to a? Well, that's just 0. That's one of the properties of integrals. And so there's this relationship between the antiderivative and the constant. And for our purposes, I'm going to write c is equal to negative f of a. And we're just going to kind of hang on to that for a second. Okay, next, let's let x equal to b, right? We're going from a to b. So I'm going to plug this back in to our original statement here. G of b this time is our integral from a to b of f of t dt, and that's going to be f of b plus c. Okay, well, we just knew from the previous step that the constant is negative f of a. So I can write the integral from a to b of f of t dt is capital F of b minus capital F of a. This right here is the fundamental theorem of calculus, part 2. This is the fundamental theorem of calculus, part 2. What this allows us to do is to algebraically compute any antiderivative, let's do this. Let's say any integral, aka area under f of x from A to B. F of B means the antiderivative of f of x at B, and capital F of A means the antiderivative of f of x at A. And we subtract them. So it's going to be a number minus a number, which is going to be a number, which is going to be an area. Okay, so let's turn the page. Too many times. I did, sorry. Okay, so here it is officially. So if f is a continuous function from a to b, then this integral of f of x dx from a to b is, here's another way you could write it. We can write the antiderivative of f, capital F of x, right? This is just the antiderivative of f of x. And then I put a vertical line here, and I say from a to b. This is kind of a standard notation shorthand. And then I'm going to calculate f of b minus f of a. Okay, now a note here is that this does not apply if we are discontinuous. We have to be continuous. Otherwise, how do I calculate an area of something, of a function that's discontinuous? I don't know how to find that area. Okay, so first example here. Oh, this looks familiar, doesn't it? So we did this the other day, last notes, because we were looking at this function. We had 16 minus x squared from 0 to 4. Okay, now we're going to do it using the fundamental theorem. Okay, so the first thing we need to consider is in this integral, if f of x is 16 minus x squared, then what is the antiderivative? All right, well, the antiderivative of 16 is 16x, right? We're working backwards so that the derivative of 16x is 16. And then do you remember what to do with powers? When we take the derivative, we bring the power down and then reduce by 1. But when we're going antiderivative, we add 1 and divide by that new power. And so we're going to get minus x cubed over 3 plus c. Don't forget your constant. Okay, so this integral here is going to be 16x minus x cubed over 3 plus c evaluated from 0 to 4. All right, so I'm going to have 16 times 4 minus 4 cubed over 3 plus c minus 16 times 0 minus 0 cubed over 3 plus c. So this is going to be 64 minus 64 thirds plus c. Then I've got 0 and 0. So I'm going to have minus c. Those c's are going to cancel out. This is the one and only time you really have to show the c's canceling out. And from now, we need to get a common denominator. Let's see, 64 times 3 is 192. Minus 64 all over 3. That is 128 over 3, which is 42 and 2/3. Or you could just leave it as 128 over 3. This is the exact area under that curve that we were trying to calculate the other day. If you remember, we did a left endpoint, which was an overestimate. We did a right endpoint, which was an underestimate. And we did a midpoint. I believe we got 34. Is that right? I can't remember. I'm going to erase that just because I can't remember off the top of my head. Anyway, that one was the closest. The midpoint approximation was the closest approximation. But now we can calculate the exact area under the curve. Okay, so let's just practice. This next one, the integral from 0 to pi of sine x. So first we have to find the antiderivative. If f of x is sine x, then capital F of x, the antiderivative of sine. Which function has a derivative of sine? It's going to be negative cosine x plus c. All right, so then this equals negative cosine x plus c from 0 to pi. So this means negative cosine pi plus c minus negative cosine 0 plus c. Yes, it's true that those c's are going to cancel. And so we have negative cosine pi. Cosine pi is -1, so negative negative is 1, minus cosine 0 is 1, so this is -1, and so this is equal to 2. Okay, so let's just make a little note here. When you're calculating definite integrals, you do not need to include c when finding f of x for definite integrals. From A to B. A little bit later on, we're going to talk about what are called indefinite integrals, which means that I don't have limits of integration. I want to just talk about the area over the whole thing, and you will need to include the constant there. But definite integrals do not. Let's do some more. We'll do one more example, and then we will talk about the other fundamental theorem. Let's turn the page. And maybe I hit. All right. So this next one, we need to find the antiderivative. So I'm going to write this as x to the 1/2 minus x to the -2, because we know about the power property of antiderivatives. So I'm going to add 1, which is 2 over 2, and I'm going to divide by 3/2. And here I'm going to add 1 and divide by -1. And so let's clean that up here. This is going to be 2/3 x to the 3/2 plus, what is that going to be? X to the -1, or just 1 over x from 1 to 4. That's the hardest part, really. And so from here, we're just going to plug in. So we're going to get 2/3, 4 to the 3/2 plus 1 over 4 minus 2/3 plus 1. I'll call that 3/3. Okay, so 4 to the 3/2, you should be able to do that without a calculator. That's 8. So this is going to be 16/3 plus 1/4 minus 5/3. So we want to get, let's see, first of all, we can call that 11/3 plus 1/4. Let's get a common denominator, 44 plus 3 over 12, so 47/12. Okay, I do want to introduce you to something that you can do on your calculator. You can actually calculate a definite integral. You can hit Math 9. And when you hit Math 9, you are getting fn int, which is going to look in a couple of different ways. If you have an old calculator, it's going to look like this. You're going to have to input the function in terms of x. You're going to have to say x is my variable. You're going to have to say my lower limit of integration. And you're going to have to say your upper limit of integration. Okay, now if you have a newer calculator, so this one right here is for a TI 83. And if you have a newer one, it just takes you right to this space. And so just like Math 8, where you just plug the things in, Math 9, you just have to plug the things in and know how to enter a function into your calculator properly. Okay, I'm not sure what it looks like on a Casio. I'm not sure what it looks like on an 89. You'll have to look that up. Okay, let's talk about the other fundamental theorem of calculus. And we actually did see it previously on the first page. We said when we were first developing the fundamental theorem, we said that if we have a continuous function on an interval from a to b, then we had this relationship. G of x was the integral from a to x of f of t dt. And what we said was that if we take the derivative of g, we get the original function, f. So what that means then, in other words, like if I want to use different notation, g of x just means an antiderivative. Another antiderivative I can write using this notation, and it means exactly the same thing. And so here's the tricky part. It's like learning a new language. We are replacing g of x with f, capital F, instead of saying the antiderivative. You can say that. Okay, and then how do I write this other thing without using prime? Another way I could write it is I could say, take the antiderivative and take the derivative. So the derivative of the antiderivative, well, duh, that's the original function. That's what this is saying right here. Derivative of the antiderivative. Well, that equals the original function. So it's really obvious, but it's easy to get bogged down in the notation. Okay, so it says find dy dx if you have this stuff happening. Okay, I'm going to show you the long way, and then we'll do the shortcut using fundamental theorem part 1. Okay, so the long way is using fundamental theorem part 2, doing it algebraically. And some of you will like this, and that's fine. Okay, so we're finding dy dx. So dy dx is going to be dy, or dt, so I'm taking the derivative of both sides here. 1x t squared minus 1 to the 20 dt. Okay, so, okay, I'm going from a number to a constant. And this thing right here is just a function in terms of t. I don't know how to take the antiderivative of that right now, but what I do know is that this part right here is the fundamental theorem of calculus part 1. 2, sorry, part 2. That's the algebraic part. And so that's just going to be f of t, the antiderivative of the function in terms of t from 1 to x. In other words, it's going to be the antiderivative of x minus the antiderivative of 1. Okay, so then let me bring this d dx business down. And d dx. Okay, what I need to figure out then is what's happening here. So let's think about this for a second. F of 1 means I'm plugging the number 1 into my function, which makes it be a constant. And the derivative of a constant is going to be 0. So what I really am working with here is, so I could write this, d dx of f of x, minus d dx of f of 1. All right, well, this is just a constant, 0. And if I take the derivative of the antiderivative, what does that mean? The derivative of the antiderivative is just the function. So that means that dy dx is equal to f of x. And in this case, that means my function f of t, which was t squared minus 1 over 20, but I'm just going to replace t with x squared minus 1 to the 20. Here is my answer. Really, it's just this part. the x squared minus 1 to the 20. So the shortcut is fundamental theorem part 1. So let me change my color here. All right, here's your shortcut using fundamental theorem part 1. When I want to find d dx of y, d dx of this integral, t squared minus 1 to the 20 dt, really what I'm doing, the shortcut is when I'm taking the derivative of an integral, that means that integral business is going to go away. All right, so here's really the shortcut, what fundamental theorem tells us. As long as I'm starting at a number and I'm going only to x, or a linear, just a variable there, then I'm going to plug that in here for t and plug that in here for t. And so I'm going to say dy dx is equal to x squared minus 1 to the 20 dx. Well, dx is just 1. And so then dy dx is x squared minus 1 to the 20, which is what we said down here. Okay, we'll just do another example, and we'll do a couple more examples, and it'll become more clear. You can do it algebraically, but it's just kind of cumbersome. So let me look at our next example. Let's go back. Let me give you another example, just a quickie. I'll just put it down here in like a little box. So for example, if I wanted to find dy dx of y equals the integral from 2 to x of e to the t plus 7t dt. I'm finding the derivative. So the derivative is a special case. So I'm finding the derivative. That means this is going to go here and here and here. And so I'm going to write dy dx equals e to the x plus 7x dx, which is just e to the x plus 7x. And I can do this because of the fundamental theorem from above. Okay, let's do another example. Okay, okay, so here's another example. It's almost the same. The only difference is that instead of x, it's x squared. So it's going to change our process very slightly. Don't be scared. Okay, so I'll do it the long way so that you can see why, and then you'll see how it's related to the shortcut. Okay, so the most important thing is to have it starting at a number and it's going to some variable in the upper limit. Okay, so I'm going to write, let's do it the long way using fundamental theorem part 2. All right, so we're going to take d dx and from 2 to x squared of sine t dt. Okay, remember that this right here is fundamental theorem part 2. This is, just ignore the derivative business for a second. This is just saying find the antiderivative of this function and we're going to evaluate it from 2 to x squared. That's what that's saying. And even take it one step further, we know that this is going to be f of x squared minus f of 2. And now if I bring down the derivative part of that, well, the derivative of x, f of x squared, whoops. All right, so the derivative of this antiderivative with respect to x squared minus my derivative of f of 2. Remember, this is a constant, right? This is a constant, so that part is going to be 0. And now I want to take the derivative of the antiderivative. So the derivative of f is going to be f of x squared. And the derivative of x squared, because of the chain rule, this is going to be f of x squared times 2x. This is dy dx. In this particular equation, we have our function is sine t, right? This is my function in terms of t. Well, I want to write it now in terms of x. And so this we would say dy dx is equal to sine x squared times 2x, aka 2x sine x squared. Here's my answer. Okay, that's the long way. This is just showing you that this works using the fundamental theorem of calculus. The shortcut looks like this. As long as you are starting at a number, you're going to take, and this part up here is variable. You're going to take this x squared and plug it in for t. So that's this part, sine x squared. And then you're going to take that x squared and you're going to plug it in for dt and take its derivative. That's this part, the 2x. Okay, so we'll do another one using the quick method. First, I have to check. I've got a number, and here I've got variables. All right, so I'm going to take that variable term and plug it in. So dy dx is going to be e to the 1 minus 3x. And then I'm going to take that same thing and plug it in for dt, the derivative of 1 minus 3x. Okay, well, this is going to be dy dx equals e to the 1 minus 3x. And the derivative of 1 minus 3x is just negative 3. So I can say, final answer here, negative 3 e to the 1 minus 3x. This is my answer. We'll do one more. First thing I notice is that I've got my number on the top and the variable on the bottom. That's a problem. So I want to reverse this, put the number on the bottom and my variable on the top. What does that do to my integral? It should make it negative. All right, so then the derivative, I'm going to write it as y prime instead of dy dx. The negative is just a constant in front. It's like negative 1. We're going to take the 3x squared and plug it in for t. That's going to be 3x squared squared. And then we're going to take 3x squared and take its derivative, which is 6x. And so y prime is negative 9x to the 4 times 6x, which is negative 54x to the 5th. So when you're first learning it, it can be confusing because sometimes we're actually like looking for the area under the curve, and sometimes we're just trying to find the derivative of this integral. And I know they kind of feel like different things. The derivative of the integral is more about just kind of replacing the notation, and the integral itself is finding the area under the curve. Let's turn the page. Okay, so last part. I know it's kind of a long lecture here. Okay, this is a really common kind of question. Now, all right, so unfortunately my graph is missing, so we'll have to draw it by hand. But it says, given the graph, there's a couple typos here too, so let's try to fix that. All right, first, given the graph of f of, this should say f of t, let me put that in black actually, so it might show up a little bit better. This is f of t. We're going to let g of x equal the integral from 0 to x f of t dt. Okay, so remember this thing right here, if I take the derivative, g prime of x is the derivative of this integral, which is fundamental theorem, and I take this thing and I plug it in and I get f of x. Okay, so the derivative of g is equal to f. All right, we're asked to evaluate some things. Okay, let's sketch our graph first because I forgot to include that in our picture here. Okay, so here's our graph, and I'm at 0, 0, and 1, 2, 3, 4, 5. All right, so at 1, 2, at 2, 2, at 3, 0, 4, negative 2, and 5, 0. All right, so it's linear, constant, and then it's like a trig curve, like that. All right, here's my graph. This is 1, 2, 1, 2, 3, 4. Sorry about the graph being gone. Okay, so there's my graph. So we're asked to evaluate a couple of things. Okay, so first, g of 0. So g of 0, if I plug in, this just means x equals 0. So I'm going to take that thing in the box above and just plug in 0 for x. 0, 0, f of t dt. Okay, well, if I go from 0 to 0, then that's going to be 0. All right, g of 1 means I'm going to integrate from 0 to 1 f of t dt. This means area under the curve f of t from 0 to 1. All right, well, from 0 to 1, well, that's a triangle. 1/2, base of 1, height of 2, I get 1. I think you can see where this is going. G of 2 is from 0 to 2. And from 0 to 2, I've got, I'm just going to write f of t dt here. I've got my triangle piece and a rectangle. So that's, maybe I'll do that in a different color. I've got a triangle and a rectangle. So that's this piece. We knew that the triangle was 1 and the rectangle is going to be 2, so this is 3. G of 3 means 0 to 3. So I'm going to have my triangle piece, my rectangle piece, and then the next piece isn't a shape. It's this curved, it's not exactly a quarter circle. I can't make that assumption. So this one's a little bit tricky. I kind of just have to estimate what this is. So I know that the triangle is 1, the rectangle was 2, and then the additional part is a little bit more than 1, maybe like, oh, I don't know, the whole, if I made this whole thing a rectangle, that whole thing would be 2. It's a little bit more than 1. Is it like 1.3 maybe? I don't know. I'm just going to estimate this. So this is about 4.2 with my squigglies, meaning approximately. You won't be asked to approximate on the AP exam. All right, G of 4 is going to be approximately 4.2 plus that other part that we're saying is below. So that's the same thing. Now here's the thing. Let me back up a little bit. All right, so I've got my triangle piece and then my rectangle piece, and then I've got my squiggly piece above, but then I have my squiggly piece below, which I'm actually going to be subtracting that squiggly piece because it's below the x-axis. And so it looks to me like those two pieces are symmetric. And so because they're symmetric, whatever their areas are going to cancel each other out. And so I'm thinking that these are going to cancel out, and this is just going to be 3. And finally, g of 5. So it's going to be the same as g of 4. The only thing left is we're going to take that, all of this, triangle, rectangle, part on the top, oops, minus part on the bottom that we already said was canceling out, and then we still have that this other piece on the bottom. Oops, I do that wrong. Like this. And it's below the x-axis, so we're going to minus that. So I'm going to have 3 minus approximately 1.3, and so we'll call that approximately 1.7. Okay, so we're going to start making these connections between these graphs and what we've talked about in the past as well. We might be asked to talk about where is g of x increasing and decreasing. Okay, so we want to remember our rules from the last semester as well. Where we are increasing, let's see, in general, any kind of function increases when its derivative is positive. And so in this case, the derivative g prime, what is that equal to? That's equal to f of x. So wherever f of x is positive, so that means that g of x is increasing on the interval from 0 to 3. And so then vice versa, it's decreasing when the derivative, which is equal to f of x, is negative. And we are negative, so g of x is decreasing from 3 to 5. Okay, what about local maxes and mins? So g of x will have a local max. We've got a local max when our derivative, aka f of x, goes from positive to negative, right? My slopes are going positive and then negative. And so do we have any places where our function f of x is going from positive to negative? Yeah, at x equals 3. And then a local min is where we're going from a negative slope to a positive slope. So g prime of x equal to the function when it's going from negative to positive, and there are none. No local min in this case, because we don't have any place on that graph where the function is going from negative to positive. It might be happening at 5, but I don't know what's happening to the right of 5, so I cannot make that assumption. Okay, whew, big long notes today. All right, I will see you next time.